Hey, you all. I'm at my dad's house. I'm not sure when you're watching this, but it's almost Thanksgiving. So, regardless, happy late or on time Thanksgiving. And I hope it was a good one. And I hope you learned a lot in this video. What I'm going to show off here is the AP banana question. There's always a lot of questions in the AP world that are infamous. And this is one of them because it gave students a lot of trouble when it came out. And I'm going to help us solve it and then also help to explain some important concepts that you'll get into more in Unit 4, but that it's good to start thinking about now. So we're not going to do the entire question because it's not necessary for our purposes, but this is saying when a grocery store opens, it has 50 pounds of banana on the display table. So we're seeing like a display table all full of bananas. Customers remove bananas from the display table at a rate, which is already a hint, where f of t is this function right here. It's saying f of t is measured in pounds per hour, and t is the number of hours after the store opened. I'm actually going to cross out the rest of this because we don't need it to answer the question we're being asked to answer, so I don't want to distract us with extra information. But it's a really cool problem because it's showing you that calculus is literally everywhere. When you walk in a grocery store and people are taking stuff and putting it back on the shelf, you're watching calculus in action. So the question here is, it's a little hard to read, but it's saying find f prime of 7, and then using correct units explain the meaning of f prime of 7 in the context of this problem. So we're given f of t, we're being asked to find f prime of t, and then specifically f prime of 7. So let's do that, okay? At this point in time, you all have the derivative skills to derive any function you're given. I'm not saying all functions are equally easy to derive, but you do have the skills if you've gotten this far. So f prime of t, well, if I analyze the f of t function, I have some constant that I know is going to derive just to be 0. And then if I look carefully at the rest of this function, it looks like I have a product. I have this term 0.8t, and then being multiplied by sine of t to the third divided by 100. I need to use the product rule. So I'm going to say f prime of t is equal to f prime g plus f g prime. I'm thinking of f and g, just how to organize my thoughts for this derivative. So f, that's a terrible f prime of t would be equal to the derivative of 0.8t with respect to time would just be 0.8, just that coefficient. And then that times the original function sine of t to the third, all divided by 100. And now we just have to derive the other part, so plus, and I'll write down here, the original 0.8t, that function as is. And now we have to use the chain rule, because I have sine, and then t to the third divided by 100 is a function in itself. We could graph that and it'd be a cubic function. Now I'm going to think about this as 1 over 100 t to the third, because it'll kind of help me better derive it. But what I'm going to do first is I'm going to derive that inside function, and that derivative, the 3 is going to come down, so we're going to have times 3 over 100, and then 3 minus 1 to be 2, so I have t squared. So this is the derivative of the inside function for the chain rule, and the outside derivative is just going to be cosine, because sine derives to cosine, and then times the same, I guess, with the same input. So t to the third, and then all over 100. So that's the correct derivative, but this question was saying, can you find f prime of 7? And it's going to be a super pain to plug into that, so we're actually not going to do that. We are going to answer that question using our technology, and then we're going to explain what did we just figure out? What does f prime of 7, this number, mean? All right, now this was a calculator question, so what I just did on the actual AP test, you should not spend any time doing. You should go straight to your device. Now I'm not going to show it off on a graphing calculator. I have done that in previous videos, and if you want me to show it off here, just message me. I'll do a little tutoring session, okay? On your graphing calculator, you would just type in this function, but you would not use t. You would just use x as your input value, but in your head, you know x, your input, represents time. And so what I'm going to do here is, one, Desmos is awesome, so I could have just said f prime of 7, and it's going to give me the answer, which is pretty great. But I'm still going to type in what we had before, just for the sake of it. So if I just called, b of t our f prime function, I just made up some function b of t and said it's equal to our derivative, and then I typed in what we had a second ago. Now, this is the same function we just derived. I'm going to actually take that off and temporarily delete it. You can see, I'll go back. You can see it's the exact same function. So what we derived, green, purple, is indeed the derivative of the f of t function. So now I could say b of 7. Again, I invented the b function, but we're getting this value, which again, Desmos gave us right away, is negative 8.11 And we should always go to three figures. I'm going to say negative 8.12. You could get away with saying negative 8.119. That's fine. But that's our answer for the question of what is f prime of 7. But here's where students really struggle because it's tough. Like, what does that mean in this context? Does it mean, like we took off 8 pounds of bananas? Does that mean we're taking off 8 pounds every hour? Like, what does that mean in this context? So let's talk about that. Okay, so we're saying that f prime of 7 is equal to negative 8.119. Again, AP test, round to the third decimal place. You could actually get away leaving it as this answer, or you could round and you would get negative 8.12. They took either of those. But if you left it at this, you actually lost points because you didn't answer the full question. The question was, using correct units, explain the meaning of this in the context of the problem. And that's hard to do, so let's talk about what this could mean. A good way to start analyzing context is to think, like, what does the original function mean? Because we're analyzing a derivative right now, but it's still important to know, like, what are the units of the original function. So if we go back to it, f of t is measuring the rate in pounds per hour that bananas get taken off this display by customers. And so when I typed into Desmos f of 7, I just got 8.407. Let's talk about what that means in this case. Let's say, just for example, each one of these bananas, like a bushel of bananas, a bundle, would be 1 pound. If f of 7 is saying 8.407, that's basically saying that customers take, about, I don't know why I'm circling all these, but I've already started, so I'm going to keep 2, 3, 4, 5, 6, 7, 8. Too many. Well, I'll say 8 to 9. They're taking 8 to 9 of these every hour. Like, that is the rate of change of bananas on this display table, right? So f of 0 would be, how many are they taking, I guess, right when the store opens. So f of 7 saying, how many are they taking by the end of the 7th hour? What was the rate of change between the 6th and the 7th hour? Maybe the start of the 7th and the end of the 7th. That gets a little tricky. But f prime of 7 wouldn't be saying, this is not saying like customers are, removing 8 bushels or 8 bundles every hour. It's saying the rate of change, which is f of t, is changing at a rate of 8 point, I'll say 12 bananas per hour per hour. Let me write that out for you just so you can see that. So what this is saying, and it's okay if it doesn't make the most sense, it's still a tough concept for me, is that 7 hours after the store opens, because again, T is representing the number of hours after the store is opened, the rate at which bananas are taken from the display table is decreasing. We know that because this value is negative, and we're actually commenting on the rate changing. So we're commenting on the rate of change of the rate of change, which is what second derivatives are in context. And we're saying the rate at which bananas are taken is decreasing by 8.12 pounds per hour per hour. I'm sorry that it's so small. I couldn't write it in more space, but the units is pounds per hour per hour. So the whole point of this video is going to be to try to make a little more sense of why this answer is what it is, what a second derivative means in context, and what is the rate of change of the rate of change. So the thing I want you to think about is, as you start this objective, what do second derivatives, like simply f double prime of x, what do they mean in real life context? So I'm not actually going to do any more problems. I'm just going to go through some concepts in the hopes that you start thinking about it. And then Unit 4 gets into this a lot deeper. So hope this is a good intro, and then it makes a little more sense as you keep practicing. So again, imagine we had some position function. That's just quite literally measuring some length of distance. So like meters, miles, as time goes by. It's describing where an object is as it moves along, okay? And a good example of that would be the classic example of, the tortoise and the hare. What you're seeing right here is a position function graph. You're seeing the tortoise left on time, seeing this green line right here, the tortoise left here, and then at the 5-minute mark, again, they traveled 2,700 meters. That's about 1 3/4 mile. It's a pretty good race. You can see at the 5-minute mark, looks like the tortoise and the hare have traveled about 900 meters. At the 10-minute mark, you can see it looks like the tortoise had traveled about 1,800 meters. And then by the end, they've traveled a grand total of 2,700 meters, okay? You can see the hare lazy, doesn't start on time, too arrogant, doesn't start until the 2-minute mark. And then you can see its rate of change to here. So all the way up here at, looks like the 8-minute mark, it's at the 1800-meter mark. But this is showing like what is the path of these creatures in this race as time goes on. This is a position function. But what's really interesting is the relationship between position and velocity. Reminder that velocity is the rate of change. It is the first derivative of a position function. And what's saying about rate of change at its most basic level is just the slope. It's literally commenting on how much is something changing, like it's changing its position by over time. Like the rate of change is just saying, how have we changed positions and how quickly have we done so? Quickly being measured, usually in time. And so we can actually figure that out by looking at, well, the slopes in a position function. So we can see in this case, the tortoise travels at a constant rate of change the entire time. That means their velocity is constant the entire time. We could just do literally y2 minus y1 from this top point all the way up here, from all the way down here. That slope would tell us the average velocity of the tortoise, and then we can see for the hare, it has a velocity here, has a velocity there. We can see it took a break here, classic part of the story. That just means at that point, it's, if I did x of t for position, and I said x prime of t, which is equal to, its velocity at that point, and we could say v of 10 right here, equals 0. It's not changed. It's not moving at all. Its position is at the 1800-meter mark, but its velocity is 0. And so last, the big point of this video is think, well, what in the heck is acceleration then? And acceleration is the rate of change. One thing I missed, remember, velocity is in a given direction. So speed is just how fast you're going. Velocity is speed in a given direction. And you can see here, acceleration is the first derivative of velocity. So if velocity is the rate of change, and acceleration is the rate of change of velocity, acceleration would quite literally be the rate of change of the rate of change. Again, we could just do some substitution with words. Velocity, we're saying, is the rate of change. So if acceleration is the rate of change, again, of velocity, imagine just putting the phrase the rate of change in velocity. It's literally the rate of change of the rate of change. It's describing how quickly is the rate changing. So to make a little more tangible, sure. Here's some example of like what acceleration is, what the rate of change of the rate of change is. Imagine you're running. Like this person is clearly has a speed. They have a velocity at every point, but you can see they're speeding up. The fact that their speed is changing, that's what acceleration is. This person speeding up, you're just commenting on how quickly is their change changing. How much are they speeding up? Like every time they're moving, they're getting to a full sprint, they're going faster and faster and faster. So commenting on the rate of change is commenting on something's acceleration. And then similarly, if you're skateboarding, you're slowing down each point. So like they have a faster velocity here, a slower velocity here, and they're getting slower and slower in their velocity. So their rate of change is changing. That's acceleration, commenting on how quickly something's change is changing. And then a reminder, if I change directions, I'm also technically accelerating because velocity is speed in a given direction, and because acceleration is the first derivative of velocity, commenting on the change of velocity. If I change directions, I can still argue I'm changing my acceleration. This graphic would be great to take a screenshot of. It'll come up more in unit 4. I'm not going to explain it now, but it'd be a great thing to pause and look at and just kind of ponder of how are these situations demonstrating slowing down and speeding up. It'd be cool, and they're funny. And so just takeaways, I want you, like, this was just sort of like a teaser video, but please start paying really close attention to the units involved with functions. Sometimes you're given a first derivative function, a rate function, like in the bananas problem we just did. Sometimes you're given a position function. Eventually we'll be given acceleration functions and be challenged to comment on the velocity and position of something if we just know its acceleration and a few more details. But start thinking about the units when you solve problems in the functions you're given and in the derivatives you're calculating. And then a second derivative is the rate of change of the rate of change. If a car's position is modeled by the function c of t, the car's acceleration would be modeled by the function c double prime of t. If a plane's velocity, how fast it's going in a certain direction, is modeled by v of t, then that plane's acceleration will be v prime of t, which we would usually call a of t in this case. And then let's say like you're quickly typing words for your college essay, and we can measure that in words per minute, which I said q of t because you're typing quickly. No real reason besides that. So let's say like the rate at which you're typing, we're measuring in words per minute. Well, the rate at which you're typing increases as your time gets closer to midnight would be q prime of t, and q prime of t is saying the rate of change in words per minute per minute. Yeah, that actually that has to be there. So yeah, it would be the rate of change in your typing in words per minute per minute. It's commenting on how quickly your typing is changing. Because as it gets closer to midnight, your fingers speed up and those words start rolling out faster. And that would be a way we could describe an acceleration in this context. And just for extra nerd fun, maybe our position function would be w of t, where we could actually just model how many total words have you typed over time and just graph that out. We could comment on the rate of change of how quickly you're typing words. And then like I just said, the rate of change of how quickly you're typing words as you get closer to your deadline. So I want you to think, start thinking about the units, start thinking about the second derivative of as the rate of change of the rate of change, and start thinking about how calculus is just, it's everywhere. Anything that is changing, moving throughout time, we can analyze with this beautiful math language of calculus. I hope this was helpful as always. And as always, let me know if you have any questions. I'll catch you all later.